Right, welcome back for the second video. Now, in the second video, we're gonna do pretty much the same thing, but with something different. So let's say that the problem is gonna be asking what's the discrete time Fourier transform of, and we have x of n equal a to the n u to the negative n. Well, not to the u of negative n. Sorry. Yeah, I just got used to it. Okay, so u of negative n. Now, once again, we're going to start from the definition. So, what's the discrete time Fourier transform? Well, the discrete time Fourier transform, once again, is capital X of e to the j omega is equal to the sum from m that goes from negative infinity to positive infinity of x of n e to the negative j omega n. So this is just the definition. We haven't done anything yet. Now, what do we have here? Well, now here we have u of negative n. So it's just like u of n, but it's like it's on the left and coming from negative infinity instead of going to positive infinity. So if you remember, we had, well, in the other example, we had this, which was the unit step. So jump at 0 was jumping to 1 and stayed at 1 to infinity. Right now here we have, well, basically the same thing, but coming from the other side. So we have the 0. We still jump to 1, but we're coming from the other side. So negative 1, negative 2, negative 3, negative 4, negative 5, and so on and so forth. And here we have 1, 2, 3, 4, 5, and so on and so forth. So instead of going this direction, we're coming from this other direction. So we are essentially coming from here and going to 1, all right, and staying at 1. So we're coming from negative infinity to 0 and staying constant at 1. What does it mean? Well, remember, just like before what we did was to change actually the boundary of the sum, and we said, okay, by using the property of the unit step, instead of going from negative infinity to positive infinity, since the unit step goes from 0 to positive infinity, we actually change it from m that goes from 0 to positive infinity. And over here, it's going to be the very same thing, except that we're going to do that from negative infinity to 0, because we are coming from negative infinity and we are going to 0, staying constant at 1. So we have that x, capital X of e to the j omega is equal to the sum of n that goes from, well, I should have done, well, it's fine. N goes from 0 to actually, sorry, from negative infinity to 0. I was almost making a boo-boo. Of a to the n e to the negative j omega n. Now, what do we do from here? Well, we can actually change the those two and say, okay, we can do from m that goes from 0 to negative infinity. And we can do that because we have a sum. We don't have an integral. With the integral, it wouldn't be so easy, but we have a sum, so we can easily do that and change this. But before I do that, let me just do one more other thing. So I wanna take care of this n and this n just like I did before. So x capital F of e to the j omega is still the sum of n that goes from negative infinity to 0 of a e to the negative j omega all raised to the n. Now, what do we know? Well, we know from before that the sum of n that goes from 0 to positive infinity of a to the n is 1 over 1 minus a. So the idea is to get to this form again so that we can solve this. Now, we actually have a problem here. We have from negative infinity to 0, while here we have from 0 to positive infinity. So how can we fix this? Well, we can actually, first of all, as I was saying, we can actually change and say, okay, instead of doing this from negative infinity to 0, we can say that we go from 0 to negative infinity, and it's going to be the first step. We can easily do that because we have a sum. We don't have an integral. With integral, as I said, it wouldn't be so easy. But with a sum, we can do that. So n that goes from 0 to negative infinity of the very same thing. So a e to the negative j omega all raised to the n. Now, we are still not happy because we want to get here and we are stuck here. So n that goes from 0, 0, okay. Something raised to the n, but we are going to positive infinity. Why in this formula? While here we're actually effectively going to negative infinity, which is not good because we cannot use this formula just yet. So how do we take care of this? Well, we can actually use a clever trick and say, let's put n equal to negative n. So now what do we do? Well, we basically change the sign of n. By changing the sign of n, what we're going to have is capital F of e to the j omega equal to n that goes from 0 to positive infinity of a e to the negative j omega to the negative n, because we changed the sign. So now we're not happy with this negative because we want it to be positive. But it's not a big deal because we can basically split those two. What I mean by that? Well, we are about to find out. So x capital F of e to the j omega is actually equal to the sum from m of n that goes from 0 to positive infinity of, well, of this whole thing. So we can say, okay, a to the negative 1 times e to the positive j omega, all raised to the power of n, basically. So positive n. So now we're good to go because we can use this formula. So we can actually say, okay, let's put this whole thing. So this whole thing. So a to the negative 1 times e to the j omega equal to p. So now if we do that, we're gonna get to this formula. So x capital F of e to the j omega equal to the sum of n that goes from 0 to positive infinity of, well, p to the n. But we know what this is because we can use this formula here once again. So this is just x e to the j omega equal 1 over 1 minus p. But we gotta remember that p was actually this full thing. So it was actually a to the negative 1 times e to the j omega. So by substituting this, we basically get x of e to the j omega equal to 1 over 1 minus a to the negative 1 e to the positive j omega. And we can basically, since I don't like negative exponents, we can basically rewrite this as e to j omega equal to 1 over 1 minus 1 over a e to the j omega. And this is our solution. So this is our discrete time Fourier transform of x of n equal a to the n u of negative n. And we're going to go on with yet another example with the next video.